no one's going to be near it. Even if we don't know what's up with the rocket, no one is going to be near it. We need to double check that everything's safe before a single person even thinks about going next to it. Cool. So we do work with commercial vessels. Some people will have to be involved, but these people will be highly trained in being around them, and they'll have all the necessary PPE equipment. So face shields, gloves, and training. We are now live. We are now live. Is the audio good? Perfect.
Yes.
Great. All right, perfect. So if anyone is near a vessel of this kind, they'll be properly trained in everything they need to do. And it will be a select few members of the club. We don't plan on just running anyone. Oh, here is our minimum standoff distances. So currently, as I said, we stand around 400 feet away because we're in M class River. I'm correct.
Between L and
Yeah, between L and M, say 400 feet. Cool. Fires. Fires are really scary. Don't want to burn anyone. And we also work with oxidizers and fuels. They will combust by the fire. Hence why we're always staying away. On site, we'll always have water and fire extinguishers. We'll never do any sort of testing without these two, and they have to be easily accessible. So before we start a static fire, we have our SOP, our standing operating procedure, on who's going to be in charge of dealing with the fire extinguishers and the water. And on top of that, every single member who is at the static fire will know how to use this equipment just in case the person who is in charge of it isn't able to for some reason. All right, nitrous oxide. We can have oxidizers near it to fight fires. Oxidizer feels not a good combo. Kind of builds off of the last one. So that's just more information about why nitrous oxide is dangerous. I'm pretty sure most of us in here are familiar with the concept. So, cool. So, believe we're boiling liquid expanding vapor explosions. It's not the highest risk with our system, but it's still risk we want to take in consideration. We are laboratory. It is dangerous by nature.
the sound is so quiet. I'm sorry.
Doesn't look like much, but concussions still very dangerous. We do not want anyone near it. Cool. Fuel air explosions. This is caused when fuel vaporizes into an appropriate volume of air, reaches a explosive threshold and gets ignited. We need to prevent this at all costs. So that's why we actually have a new position called the safety lead. The safety lead is actually in this room. His name is Sam. He's in the back. He was just elected today, so he wasn't put into the slides. But safety lead's position, he's making sure that whenever we're doing a static fire, that the people in charge are doing the right things. So while let's say Chris is trying to ignite the rocket, he's going to have his own separate checklist that is exactly identical to his, and making sure he's not skipping through all these things. Because we need everything flowing as it should, when it should. Electrical hazards. Just like with anything nowadays, there's wires, electricity's flying through it. We need to be really careful about this. Electricity, it can ignite things. You don't want anything prematurely ignited. Really bad for us. So to do this, whenever someone's working with any type of electronics, let's say on the rocket or on the GSC, we are making sure that they know exactly what to do, what not to touch. If they don't need to touch it, they're not going to touch it. Burning. So this one doesn't just apply to the rocket and everything that can be caused by the rocket. We live in the desert, and we are working with metal frames and metal rockets. Simply touching the rocket when it's 110 degrees outside is going to burn you. So having the proper PPE like gloves is a must at all times. So if anyone is planning on being near the rocket, they're going to have gloves. That's the next one. And frostbite. Virgin frostbite on the same rocket. Don't you just love science? So, nitrous. it pulls down whatever it comes in contact with. So just like with burns, everyone needs to have gloves on at all times. And if you know that it's running through, if nitrous is running through that pipe, you aren't going to touch it. Or if you don't know what is running through a pipe, you're not going to touch it. And that falls onto the safety lead to make sure he teaches everyone what is happening within the bucket and how to safely deal. Fumes. So for this, we are trying to create an SDS, safety data sheet on how to deal with all the chemicals within the lab. We want to know that if fumes get into the air, on how we're going to evacuate the premises and how to deal with them properly. Since no one in the club is properly certified to deal with fumes, this is what we call a certified person or have someone by who does know how to deal with these chemicals. Any questions about safety? I've heard. Oh,
Sorry, yeah. So I know there's probably already looked over, so I'm just curious. There's different classes of fires, A, B, C, D.
yes.
Right?
Yeah.
Sure. I'm just curious, you know, or say you need to know how to identify and do you have to write?
Yes. Most members in the club are actually OSHA certified.
Wow.
So that's been a real plus. So some people already know how to classify it. And it's also something I'm planning to teach at a future general blind meeting, probably the next one. Like you said, fire classification is really important.
I'm not sure, honestly, as a talk to you about, but like really kids and they can be started higher in January. That would be interesting. I know they have that. And also get by competition in May.
In January,
Yeah, because that's supposed to be our first static fire.
You're going to the symposium in January.
yeah, we'll always do some code. I'm not quite sure on the static fire, so I'm pretty sure we can figure out more stuff. Okay, and then we could talk more about that. Okay.
Do you guys have any like safety certifications you guys get to students? Like, is there any courses you guys got?
So we don't currently have our own safety certifications, but that's something I was trying to look into. Maybe try to get more people certified in OSHA 10 since it's a relatively easy thing to do.
Yeah.
But that's something I want to work with the U of A to see how to figure out to get a bit more efficient.
Yeah.
Yeah, but right now at the moment, it's just we're figuring out this whole safety thing since it's a brand new position. So we're gonna figure out.
Can you describe a little more of your, I think the term you used was the electric match?
So yeah, E-matches, that's how we ignite the rocket. So, just in case that short circuits might go off. Pretty.
Yeah, so how does it actually work? What I'm
Yeah.
getting at is, do you need certification just for that?
So the E-match is a very small pyrotechnic device, about this big. To ignite it requires in the range of hundreds of milliamps current, very small. You can even use 5 or 9 volts to do so. When it does ignite, it's just a small pop. It is technically not safe to be super close to, but it's very, very small and contained. They're used to ignite typically much smaller solid rocket motors, which in our case, same ignition system will be used in this rocket, more on it later. Very small, and that'll be in here. So when we're handling those, we keep the end leads shunted so that any static that builds up as we're working in the heat in the desert, wherever we are, will not go through those leads to ignite them because with that low current, they can be sensitive. Otherwise, they have protective little coatings on them, and we keep them in a secure box while in our club area. So to mitigate risk.
Good, certain things I was hoping to say about, refer to grounding, also basically shifting things like that, so you have to take special training in order to go into those.
As of this moment, no.
No, you can just buy them online.
Yeah.
And they just get shipped.
Is there a class that people like to, and helps is when the pitch organization classifies them, but I would.
In my knowledge, no.
No, I haven't read any classes on it. Because you can kind of just buy E-matches anywhere. Like we get ours off of Amazon and CS Rocketry.
Yeah, I think it's because they're very small.
Yeah.
I've seen higher classes for bigger solid motor, but not even the little solid motor we put in there is not classed as an explosive transport.
Well, would you consider this the first rocket and the second rocket that we've had over years? Is this
Yes, this
This
is
is the first.
Yes. The Sonoran Wildcat, first rocket, these are the same thing that you see right here.
And then you're just gonna completely start off, because I know the rocket has to come back down and slam on the ground, and you're just gonna start up status, or do you have a
For recovery or for the whole structure or?
Not for the whole structure, or like whenever we launch, because I know we have to launch it from our guys want bring it back down and land it. Are you gonna set the platform for the landing platform to come back down like from scratch, or do you have a plan for it?
We are not landing propulsively, so we don't exactly have control over, we don't actually have any guidance other than, and we'll talk about it later, looking at roll stabilizing. So as far as landing platform, that would be out in the desert at FAR.
Right.
So
It's just a glorified height.
the recovery system will be very similar.
Parachute.
Yes, parachutes with very similar recovery systems, whatever testing actively with this one.
I thought you did a really good job on safety things with nitrous oxide and the risk of oil explosion. Something that was not discussed there, and I just want to make sure you're aware of this, is it's super critical nitrous oxide.
Yes.
You know, yes, that's an important thing to look into. Supercritical nitrous oxide is typically what like commercial nitrous oxide tanks are designed to withstand.
Yeah.
As I'm sure you know, nitrous oxide has a very strong pressure and temperature range. And I don't know if you look into the supercritical nitrous oxide risk, because at this scale, and I know you're familiar with the home built pressure vessels at
Right.
4 inches. As you scale up, that comes out 30 inches. Yeah, I would look into that.
That's something. Like Sam, right? I think. Any more questions about safety? We'll take this as last one.
When you say OSHA certified, like, what do you mean? Because I noticed with the electrical, packaging and designer.
Yeah.
But that it means like electrician apprentice OSHA certified, like, do you say that? I just want to know, like,
I see what you mean, but when I'm like referencing OSHA certifications, I mean like it varies on OSHA 10, the 10-hour program. But let's say like in your case,
because I've been.
That's more-
many SCR classes.
yeah, so if anyone has any type of like safety certification, it's equally as good.
That's kind of.
Yes. No, that's a good question. I'll definitely think about that. All right, that's all for me. And next up, we have the engine.
Hello, I'm back. Okay, so now we're into the subsystems. As you can tell, they sort of get progressively shorter as the slides go on, but we're starting with the engine, arguably the most important part of the rocket. These are the list of requirements. I'm not going to go through all of these, but I'm going to go through a couple to explain them. So a very important one, the engine shall not sustain permanent damage from firing. We want this rocket to be mostly reusable. There are some exceptions to this. Ablative liners are the big one because it's the simplest way to make sure the engine doesn't melt by sacrificing some material to it. Let's see. The nozzle throat will be something that doesn't erode. So this is key for how we measure thrust. As of right now, we don't measure thrust with a force sensor, we measure thrust with chamber pressure. And this is good provided you know the right parameters of the engine. One of those parameters is the throat area. And if the throat area is changing, then you have a much harder time getting an accurate thrust profile. So we'll get into this later, we're looking at either graphite or some kind of. And let's see one more. The entire engine system needs to fit within a 6-inch diameter. This 6 inches is the diameter we're setting for the rocket. And we need to make sure that nothing sticks out of 6 inches because it will cause challenges for integration and drag the flight. Okay, so a little overview of the engine. You can't see this very well. Oh, I'm sorry about that. Oh, actually, could somebody hit the lights? That might help. Yeah.
Not much better.
That did not. You can turn that back. So 1,000 pounds of thrust. Again, that's about 4 times what this makes. It's technically higher than it needs to be, but we like a good margin. Ablatively cool. If you could see this, you would see that there's a tube made of ablative, and it's about 0.4 inches thick, which is quite conservative for our length of burn. Burns for about 8 seconds, but It might burn for less than that if it burns higher thrust. We'll get into that later. Chamber pressure about 300 to 400 psi. This is sort of limited by the properties of nitrous oxide. You can only get so much pressure into the chamber based off of the vapor curve and everything. Ideally, a metal nozzle. We'll get into that later. And of course, this is a rough design. The most finished part is the injector, I would say. So comparing the two, on Sonora Wildcat, we used a heat sink cooled engine, which means the chamber wall is 1/2 inch thick. And that is simple, it's very reusable, as long as you design it right. But the catch is it cannot burn for longer than it's designed because then it will get hot enough to melt. Heat sink means it just absorbs the heat and distributes it evenly. On the new rocket, it will be ablative cooling, which is burning away material to take heat with it. So it's not reusable. On this rocket, it was a simple manifold injector combination with a screw pintle injector. It's easy to manufacture, it works pretty well. The new rocket, we're hoping to get a little bit more efficient mixing from a impinging injector with higher symmetry. This rocket burned very cold in the engine as far as rockets go. The new rocket will burn hotter and but hopefully also higher efficiency to get more performance. So some numbers to back that up. We've already covered this. The throat diameter, you can see it's almost double on the new rocket. The specific impulse might be higher. We've tested to 140 seconds. Specific impulse is a measure of efficiency. On this rocket, that was the highest we ever got. The simulations say 160 seconds, but I'm skeptical. But that's okay. That's why we tested it. Chamber temperature, big difference, 1400 degrees Fahrenheit versus 2600 degrees Fahrenheit. That's exactly, no way, you can't say that. Never mind, I was gonna say it's twisted, but it's not. Here's a size comparison of the two new engines. I think this is quite illustrated. You can see the engine down there. Well, maybe you can see it later. It's among the fins, but it's this right here. That's what this is. And so this has got a copper throat as well and an aluminum liner. This was modeled as an all copper throat, but our preliminary simulations say that's not necessary at all. Chamber, it's bigger in every dimension. And then this is the pintle injector we were talking about, and that's going to be the new injector, which we're going to talk about in detail now. So this is a pintle injector. This is a impinging injector. It takes fuel in the center. The reason for that is because the fuel tank is at the center, so it's more convenient. But there's whatever. And then it takes oxidizer in through here, and it goes in this annulus around to distribute to all of the holes. These are the holes that shoot the fuel in. These are the holes that shoot the oxidizer in. You can see they're both angled so that they will meet and impinge, as the name suggests. It's got bolts it's got the injector plate as a separate feature from the manifold, which allows the injector to be replaced if it turns out our models were wrong on the injector hole sizing. You can also see how the oxidizer is much bigger than the fuel because of our oxidizer to fuel ratio is about 4. That's for mass, this is for volume, but it's pretty close. Here's what the injector looks like in 3D. You can see these rings of holes here. They're all pointing at their corresponding fuel and oxidizer hole. These bolts are how it's bolted to the chamber, because the chamber will just be a tube. And then you already have to talk about that. Sure. Just real quick.
So I did I used a little bit of ANSYS spoon to find the heat flux as you went through the chamber. So I set our inlet conditions here. And then, so from that, we're able to have a CFD model, which is not pictured here, that showed how the pressure and temperature rise occurred through the throat. And then we modeled a couple different materials in transient thermal.
So this here is copper, and this is at second 8, and you can see the temperature, propagated out much farther in the nozzle. And this is stainless steel, which we're kind of leaning towards, right, at the moment. And you can see it put a lot more effective, there's a lot more effective burn in there. This is a really cool kind of simulation of the burn of the thermals of the copper. So, right here, or before it started at second 0, and then as it goes, you can see the throw heats up quite a bit, all the way up to, I believe, 1600 degrees Fahrenheit.
Okay, this next slide is sort of illustrative. I don't have any specific numbers to point to, but if you want to take a look at the slides either before now or after now, these are the numbers that we calculated. We've already talked about all the important ones, so there's not too much to say on them. So these are the preliminary half-cat sim results for our new engine. Half-cat sim is a rocket engine simulator written in Excel. It's kind of glorious, if I would say so myself. And you basically get to put in all of the physical parameters of the rocket, like how big is the tank, what are the injector holes shaped like, and then it comes out with these graphs of thrust curve and pressure chart. And the pressures, it just sort of shows you what pressures we're dealing with in the tank and the chamber. And then the thrust curve is the thrust versus time. So you can see it goes out to 8 seconds. You can see the simulation suggests that the burn is higher than expected. It's about 1300 PSI or 1300 pounds, and it burns for shorter, which that would make sense. A higher burn, shorter time. This dashed line is our 1,000 pound burn. And what that suggests is that our models for the pressure drop across the feed system are conservative. Relax it a little bit. So this is a comparison of the two thrust curves. In orange, we have the new rocket all the way up here. And this in blue is the test data we have from our 4th successful, I don't know. It's our most recent static fire. And you can see the new rocket, it burns for longer and it is higher thrust. Overall, much more advanced. Okay, questions? This is a big topic, yeah. So, yeah.
I have just about the bell. You showed that you were preferring, I think it was stainless or was stainless steel versus
Stainless steel, yeah.
Stainless steel versus copper. Why is copper had, I don't know the proper terminology, but it had like that heat gradient pull off of the bell, and you preferred the stainless steel to a smaller gradient, like closer to the skirt of the bell? Why is that necessarily better? How does that affect?
So, that's a very good question. I'm glad you asked that. It's not necessarily better because of the heat gradient, but what the stainless results showed us right away is that we could, in principle, in quotes, cut out most of the mass of the nozzle because most of it stayed ambient temperature. And so we can make the nozzle much lighter, and that's good for the rocket. With the copper, that might theoretically be possible too, but stainless is also in general cheaper. So if we had to choose between the two, we always got to balance mass versus cost. And we like things to be cheap because we don't want to run out of money.
Cost plus manufacturability as well.
Mm-hmm.
Especially when considering graphite. Yeah.
Yeah.
So when you're early on, so Sydney or anatomy, what was the some points because I got for acting and the pressure.
Yeah, it is acting. Half-cat sim is what validates our sort of design calculations. ANSYS is what we were using for the nozzle thermal. That's a whole can of worms. And then to design the rocket, we have a kind of integrated with half-cat sim. We made a custom rec design spreadsheet that calculates all the numbers based off of a whole bunch of inputs, which is what I posted in those slides, a few slides back.
Yeah, you first started this section with the requirements for the engine. What was your guys' process for what they called it?
I mean, we sort of just, we say we want to build a big rocket, and then the requirements sort of just come out from what is needed to make that happen. So, like, for example, in our case, big is 1,000 pounds thrust, and 6 inches diameter. And
We wanted to base it also on the half cap principles of the pressure, which we'll talk about one later. But going by that as a baseline, as well as things like impulse, thrust, those are what top level dictate other parameters down the line, including budget.
yeah, budget is, there's always a lot of factors that go into any decision.
So maybe one in charge of budget, how much do you think, well, we already have the first thought here, how much would budget be set?
Entirely depends on what you want to do. There are multiple schools of thought for developing rockets. You can develop very big rockets, or you can develop very, smaller but very, very well mass optimized rockets. And both of these things can achieve similar altitudes if you want to. The current liquid rocket record altitude holder was actually almost like smaller than this. But it achieved that by being extremely optimized. It had no frills, no extra, nothing. And it was just all tank, So
Do you know how much the height was on that?
it was around 20,000 feet. Okay. I'm not exactly sure where the current record is because it's not well kept, but it's, I think, less than 30,000 feet. We'll see. Yeah.
This is kind of like the mixture chamber and such, but why is there a big gap between between the tank? Yeah, between stuff. Because I'm thinking if you could 3D print a shower, you could do something better that's resistant to the heat, temperature, pressure difference, then you could probably get it closer to 1,000 feet. But I was wondering about safety, if that would have to do with the compensation of
It's, you 100% could, and people do. We just haven't because we don't care, I guess. Like, I mean, the point here is not to be performant. The point is to, to learn a lot and to just learn. And we've thought about, you can just 3D print something and it would probably increase performance a lot, but yeah, we might eventually. Yeah.
So besides changing the covers, Steve, what other monarchy have you done that's not that so
For the half cap rocket or for the current design?
yeah, this is based on Mohammed, right?
Rough. So this was mainly in terms of the piston design. All the other engine things are different. For example, this was a heat sink. This is ablative. So as far as my knowledge at least, we basically use the tank feed and pressure design. But other aspects about the engine are our own. Correct me if I'm wrong on that.
Yeah, we're not using, this rocket is a by the book. Literally, there is a book about how to build this rocket. And for the most part, we followed it. We changed things where we felt like it, and including adding stuff for safety. But the new rocket is a totally like, we're making all the design decisions just based off of sort of principles, but no specific numbers. Yeah.
So for the length, are you considering helpful? Are you considering changing it for the new rocket? But say it was like, don't worry about the budget. Would you want it to be bigger or keep it the same size as that?
I think your question will be answered in not the next section, but the section after.
Okay.
So I'm assuming the end is gonna get really hot with this whole system. Are you worried about the metal morphing or expanding too much? You have a cooling system of any kind? Symptomatic?
Well, yeah, the heat is the big thing we are concerned about. And the cooling is the ablative, but it's also just allowing the heat to soak in. We have to save a lot of complexity and weight. we have to model stuff as like the transient effects of the engine only burns for 8 seconds. So you only have to make the engine survive for as long as it's designed. If you were to burn it longer, it's outside the scope and it would be allowed to melt. But so yeah, there's a lot of thermal considerations, but yeah, I don't know. It's all wrapped in there. All right. Oh yes.
All right. So I've got some notes here.
Sure.
So first of all, I noticed when you were talking about your engine requirements, you did not have any mass range target requirement.
True.
I especially noticed when you then showed off your nozzle models, which included one made out of solid copper.
Yes.
Okay, we'll get to that. First of all, why 16 by century? Why is that a requirement?
Yeah, I was actually talking to people about this just before the meeting. It seems like it shouldn't be a requirement. It should be a like design choice. I think I wrote at least just to because the numbers for how big the holes are suggest that it would be very manageable to hit 16 for the machinists. But yeah, you did bring that up, and we did talk about that before. The mass. So the nozzle design is not finished mostly because of thermal sims, we don't know what we need yet. So what I modeled in there was basically the absolute worst case, as big as the nozzle could be. I'm sure it weighs like a lot of pounds, but as a sort of, we don't have a specific altitude target. So a specific mass budget, we don't have at this time. We'll probably impose one eventually, but ultimately we sort of decided that it was better to not impose a mass budget without knowing roughly without knowing what the scope is, because we don't know what a similar mass budget would be because we've never built one like this before. It's just the rocket is not goal to fly high, it's just to fly long. So that's the primary kind of directive. The primary.
Good answers on that. Can you bring up the numbers slide, the spreadsheet?
The spreadsheet? Oh, yes.
I was looking at this earlier. And while you bring it up, main question, which is in direct relation to the spreadsheet, what thermometry software do you use?
So Half-Cat Sim does thermochemistry itself, specific to nitrous oxide and a selection of fuels. And it is well anchored in real fired engines. The sim is not just, in a vacuum, it is calibrated with a bunch of other engine data. And so right now, I have this set up feeding between Half-Cat Sim and the design spreadsheet to get the right thermochem value. It's also checked with NASA CEA, and I tried using RPA, and then my free trial right now, so
Okay. It's good to know that you're checking this with NASA CEA, because what immediately stood out is you have a 4-to-1 mass mix ratio.
yeah.
That's very close to stoking back.
Mm-hmm.
And your predicted chamber temperature is 1700 Kelvin.
This is
very low.
It comes from the additional pore mixing efficiency. That's not the ideal chamber temperature. That's with like some efficiency factors just slapped on there to account for the fact that most of these style of engines don't perform ideally at all.
What is it using to determine what the efficiency factors? Because you've also decided in this design to go for unlike infusions, injector, which is going to greatly increase your adaptation.
Mm-hmm.
The reason I'm worried about this is because you were already concerned about thermal issues with the nozzle.
Yeah.
And that's with the predicted chamber temperature of only 1700 Kelvin, which it's been a while. Off the top of my head, that's like at least 1000 Kelvin below what you should be expecting
With the idea.
yeah, that's 4-to-1 ratio. So I just want to make sure that you're aware of that. And it'd be nice to see some consideration during the testing phase for if you do have higher combustion efficiency, which in many cases is great, right? It means you get more bang for your buck. That you have contingency plans for that from the thermal management side.
Yeah.
Because as we're getting to, if you can go to the work calculations, go fast.
Same. I did it slide.
Yeah, the nozzles, yes.
Yeah.
It's like go fast. It's not great already. Like when we're talking about stainless steel,
It's true.
It's like 1700 degrees Fahrenheit. That's like
It is close.
that is and that's close with your lower combustion temperature, and that's with a solid stainless steel nozzle.
Yeah.
So I want you to consider the fact that you seem to have converged on one metal nozzle selection, but you're being I think that you think you're being conservative from a design standpoint for assuming lower efficiency combustion, which is true when you're talking about performance.
Yeah.
It's not when you're talking about efficiency. I think you should be assuming that you are going to combust at close to high efficiency, especially because I saw that you gave the made the L smell long enough, made the chamber long enough to allow for full combustion efficiency. And you're still assuming that it's going to be much colder. And I think that that's a potentially dangerous assumption. It's probably going on. The other thing I wanted to point out here is you did mention that you could reduce the amount of metal based on these assumptions. However, metal conducts a lot of heat. And I would posit that even the cold parts, right, even the blue areas in here, in the simulation, they're still looking large amounts of heat away from the hot surface. So I don't think that you can say, oh, right, look at the through portion steel, we get rid of all the blue section, the heat and the rest of it's going to be the same. I think you cannot make this. I'm sure you can leave it at this test. No way to figure it out. And speaking of thermal management, can you go to the injector design? I have a couple things to. So I have two main concerns with your decision to have the fuel input, the acid input, and the oxide.
Yes.
The first one is you do not seem to have any film coolants.
True.
Which means that, and especially if you're considering an inefficient combustion process, it means your oxidizer rich section of the combustion flow is the one that's next to the chambers.
Yeah.
That's the opposite way you want it. If you're not going to have good mixing, which you can sometimes do on purpose, with the fuel to be on the outside, because when fuel takes heat, it vaporizes and turns to soot and protects chamber wall. When the oxidizer takes heat, it tries to attack anything oxidizable, which includes your chamber wall.
Yep.
So
I was trying to figure out why everyone puts fuel on the outside.
yes,
And that answers it.
and there's another reason why they might do that. Tell me, do you know what is the average flow velocity in your oxidizer input manifold?
I can tell you what the injection velocity is, but
Yeah,
not
that's what I
the.
figured.
I mean,
So here's an important bit of detail when it comes to oxidizer, when it comes to this manifold design. Your oxidizer, the fuel input, you don't really need to worry about pressure difference between all the different holes because it's all asphalt. But your angular manifold, then, at least in this design, you're only putting the oxidizer in one side. As the oxidizer flows around that manifold, it's going to lose pressure because you have more at the beginning, less towards the edge. that means that you're going to have more oxidizer injected at a higher velocity, closer to your oxidizer than you are on the opposite side. And that can obviously induce a non-axial injection, create a hot spot, create lots of that.
Yeah.
So so when I was doing this, yeah, by the way, for everyone that doesn't know, I was a former president of this club 2 years ago. So there's the rule of thumb that I was taught. I want you to research this so you don't have to go out the rule of thumb that I told you. Is that if your average flow velocity in the outer annulus is less than 10 feet per second, you generally don't need to worry too much about pressure drop between the different place. But just looking at this, I can tell you that especially with the oxidizer, which has 4 times volumetric fuel rate, that is not a large enough manifold.
Yeah, so you could just make a manifold.
You can just make the manifold larger, but I want you to look into how much it is, and I also want you to potentially examine and trade your design to have fuel the axial and oxide, not the axial. Which are really these two things. Oh yeah, I have one more point. Did you go to your habitat simulation?
The thrust curve?
Yeah, the thrust curve simulation. Yeah. 850 psi starting pressure.
In the tank?
Yeah.
Yeah,
I thought you were doing autogenous pressurization.
indeed.
Okay.
That's for hot desert conditions.
It is for hot desert conditions. All right. And the simulations you're using modeling the density decrease you're going to get with nitrous oxide at those conditions.
Yeah.
Okay. Just want to make sure.
Well,
Yeah.
I don't have anything to say. All right. Any more? Or are we moving on?
Feed system. Yes. So we're really using servo actuated ball valves for all of ours, as opposed to solenoid valves, which are more expensive, have a lower mass flow rate, and take up a lot more space. And with the oxidizer, they're having a lot higher mass flow rate. You're increasing the size of our ball valves, the that portion of the rocket. And all of our onboard valves will be controlled by the rectangle, which we mentioned more later in the presentation. But it's our flight computer. And so these are the valves from our old rocket. These are 1/4 or 1/4 inch ball valves. And for our new oxidating valve, this is the preliminary design. But after further testing of the ball valve, another actuator assembly will be needed, which is currently under development. And it needs to be 1/2 inch instead of 1/4 inch because of the high mass flow rate. So yeah, this fill systems. This is a nitrous oxide tank, and then that is controlled by our servo here, PC. And then we have an off gassing here that runs to the nitrous oxide tank here. And this is a good representation of the concentric tank that we mentioned later. And this is a SketchUp of our RCS system, which is controlled by 2 servo controlled valves. So they will be controlling counteracting RCS thrusters like this. And then we have our oxidizer, which we'll have here, and our igniter here with a pressure transducer directed right into the combustion chamber instead of this previous point on this rocket, right next to the igniter, right on the igniter. Yeah.
But it's something. Yeah.
So the nitrous is self-pressurizing, which means we don't need to have a fuel pump or anything. So with our tank design here, we have the nitrous oxide at the bottom and the fuel at the top. So you can really get an image of this on the next slide. But there is just a piston here that the nitrous oxide evaporates and creates that positive pressure. It pushes that piston up that has dual O-rings and it forces the fuel out the top, where we have this ball valve here, and it's directed back into the engine.
It's actually this.
Yeah. So yeah. The biggest thing that Kevin kind of touched on earlier is we really do not want the oxidizing fuel to mix inside the tank. So while it does sound a little bit sketchy, it's just a piston that has two O-rings and it moves up and down as the fuel drains, and you have a positive stable pressure here at the bottom. And then this is a good illustration. So this is before fill. We'll fill the fuel before launch, and then during or before we get to the pad, and then here we'll fuel the nitrous oxide. We'll put in the nitrous oxide. We'll compress the piston there, and as we fire, the nitrous oxide will drain. The positive pressure will be maintained here, and of course the fuel out. And then at least when firing, we'll just have entirely gaseous nitrous. Any questions?
So for the piston, does it need any lubrication? I suppose it's straight the metal inside.
It's designed that for a moving piston seal, you need the metal wall of the piston to be, set in from the metal wall of the tank, so there's a gap, and then that gap is filled by the fuel. It's a pretty small gap, but yeah, it's the only thing touching the two things is the other.
Okay.
No lubricant so that nothing can be touch the
There is
oxidizer.
lubricant on the over.
Right.
The grease.
Yeah, not much so it doesn't ignite, can't mix with the oxidizer when
It is
travels.
so it's not
Right.
made from fuels. Right. Yeah. Anything else? Yeah.
I know you have an answer for it. Okay, so I want you to say it in review. What's your solution if you lose contact with rocket? The pressure?
Yes, that was what I touched on. My apologies. Yes. So we have a manual control valve there, and it's a really good illustration of it very early in the
It's back in the safety.
Yeah, but there's just a string and you pull it and that works. And this
It's
is
a very, very long string.
yeah, and pull that one goes up. So
Prior rocket had a static vent that would always be venting nitrous. Current rocket, we want to maintain more of the nitrous in the tank. So we are ditching the static vent, but we are continuing to keep the manual dump valve if needed in the case of a valve or electronics failure.
So we'll use the RCS thrusters as vents.
Additional.
Because right now on this rocket, there's just a small hole here that's the nitrous oxide.
This was when setting up a launch pad and something goes wrong, you just say, okay.
Correct.
Yes.
Yeah.
Yeah.
Assuming we are off the launch pad, something has probably gone right, and we are probably already venting the valve.
Yeah. Actually, I can't say this. We'll get into it in the RCS section, but it probably won't. Never mind. We will get into it later.
Just to be clear, there is a radio link between the PC on the ground and the rectangular flight for data acquisition, things of that nature.
We'll have more on that later.
Yes.
Any other questions?
Up next, tank.
Up next is tank. All right, I guess I'll get to that tank. All right, so the tank is what holds the propellant. We're going to make the tank 6 inches in diameter, and that will be considered sub-minimum diameter. Like this rocket, the tank, the outer wall. There's nothing protecting the tank from the airstream. The tank will be concentric, which we have some good illustrations to get into later. The tank operating pressure will be 1045 psi, which is an important number. That is the critical. It's critical, right? That's the critical point. I was going to call it the triple point. It's not that. It's the critical point of nitrous oxide. So, meaning if we exceed 10,045, then that means we have to stop and invent the tank.
Abort, don't get rid of that.
Yeah. We'll have radial bolted tank, just like this is. You see the black bolts holding the bulkheads on. And as we talked about, it'll have a dump valve to be present. And we have more requirements. Redundant O-rings kind of goes without saying. If one O-ring failed, we'll still have a backup. This is a big one. The tank will not be bigger than what could provide the impulse under best case scenario for more than 40.96 kilonewton seconds, which ultimately means we want to keep this rocket legally classed as class 2. If it goes above that number, it's class 3. And if we go over that without knowing, it's a huge amount of paperwork. If we go over that intentionally, it's just a lot of paperwork. And so we want to stay well out of that. So that's our limit. An additional practical limit, the tank cannot be longer than we can transport. Right now, that's a 1,008-foot limit of the longest car/truck bed we have available to us. Yep. So we got pressure transfers without the tank. So here's some more comparisons. They're the same thickness, 0.125, that's 1/8 of an inch. And that does mean a lower burst pressure, but it's still more than double the MEO. So it is okay under far out rules. Then we have obviously the concentric tank, which we're getting into. We'll need to have more radial bolts, but it's a bigger tank. There's more force on the bulkheads pushing them out. Impulse class about O. We're definitely not going higher than that. So what is a concentric tank? So the Sonoran Wildcat uses stacked tanks, which this will make a lot more sense on the next slide, where the fuel sits on top, the oxidizer sits on the bottom, and the piston sits in between. The piston moves upward during the firing. What we're going to do is concentric tanks, where the oxidizer, there's the main tank wall that holds the pressure, so the outside. Inside is a smaller, non-pressure bearing tank, minus maybe like a few dozen PSI. And that holds the fuel in the middle, the oxidizer in the annular region around it. The piston starts at the top of the fuel tank, which is also the top of the entire tank. And it moves down with flight. So the main advantage is that both the fuel and the oxidizer come out at the bottom of the rocket, which is where the engine is. And we have gaseous nitrous available at the top of the rocket, which is where the vents will be. So what does this look like? This is to scale, these two, and those are to scale with each other, but obviously not with this. This is the tank of the current rocket. You can see it there, and you can see this portion of the rocket is the tank. This portion is the recovery system, which we're not talking about. This is the new rocket. This is the 8-foot tank. We might yet downsize to a 6-foot tank under transportability concerns. And you see oxidizer here, fuel here, and then oxidizer here around, fuel in the middle, and it runs up the length of the tank. Bulkheads, these are a more preliminary design, but the general idea is here. There are radial bolt holes here. We might decide to move them here and have them go through, but that's a design decision more than anything. We have O-ring grooves, 4 grooves, 2 for the fuel, 2 for the oxidizer that go all the way around, which you can sort of see here. And the fuel tank, which is not modeled, I should have, this would make it less confusing, rests on these O-rings around it. Then the oxidizer rests around these O-rings. Here we've got more numbers. Okay, moving on. Any questions? Yeah.
So I'm just curious, is the tank lined with anything on the inside, like some kind of liquid pulpic material?
Nope.
No.
It's just raw aluminum.
Because I'm trying to figure out what transportation. Can you have any type of transportation, like, or you just think like car?
Oh,
The car is like, if we do make this 8 what are, so what do you have a plan on like your transportation?
well, some people have trucks. Some people have trucks with long bends even. Some people also have like SUVs or whatever, that we could put it up and then onto like the thingy from the car. Ultimately, it's just up to what you can manage. University of Tennessee, Knoxville, they were out far out last year with their rocket titled Big Liquid. And it lived up to the name. It was a class 3 rocket. And this tank was 9 or 10 feet long. And they got around this because they own a trailer. The trailer is more than long enough to carry the tank.
So if we had a car that we ran, that would be different.
Yeah.
If we, if that was not.
It's a logistical problem more than anything else.
It helps to disassemble parts like the recovery. Like for example, here we have the entire forward payload recovery section removed. Worst case, you could probably even take off parts of the engine if you really need to minimize that length, but otherwise logistics rather than.
Yeah. Okay. So touching on that, the application, was there anything you did like installation around the transporting that you're trying to turn that car, let's say, what would you say about
Well,
that?
the tank is transported empty. So, if your car gets hot enough to deform aluminum, I would be concerned. But that's pretty hot. I mean, it might not be as hot as you think, but it's hotter than it's likely to get. So, I mean, it's aluminum. It's pretty hardy. Yes, it's not fragile like anything like that. It doesn't require pressure to hold its shape. Some rocket tanks are designed like that, but not this one.
The most sensitive parts were honestly electronics, which we would, if it were a battery, for example, a sensitive lithium battery, we would just keep that in the bay where people are, and if people are uncomfortable, so will the battery. But otherwise, the servos are well within thermal range, especially without being on. So as far as the structure of the tank, totally fine.
What is the plan to support the concentric tank?
It'll be supported by both bulkheads at either end. The top bulkhead is still it's not finished being designed, but it will be similar to that, except with the addition of allowing nitrous pressure to flow over the top of the center, because that's where the missile is, and it's the pressure out of pushing down. According to people that have built this before, that is more than enough holding for a concentric tank.
It looks from your design like you're going to hold it like you're not.
Yes. No, but we just needed to illustrate that pressure would flow over the top. It will be held at both. If not, it could be held sort of in the middle, but it's still too far. Yeah.
For our club, we just started sort of building out the organizational structures as well as technical components for it. And so my question is more of like the first side. And with like training, do you guys do cross training, or is it just like you have to kind of set teams and you just build, or you do like workshops?
I'll be honest, we're still organizing our club too.
Oh, okay.
That's kind of the point of this year, to reorganize the club into something that works a bit better.
Okay.
But so far with this year, I think like having a bunch of sub teams that specialize in one thing has been pretty good.
Okay. Perfect.
So this is a great topic to talk about after the propulsion engines.
Oh, yeah.
All right.
Okay.
Kevin has a question.
Okay.
What's your oxygen giving procedures? I know you may not have gotten to that stage yet, but I'd like to see at least an
You're right. That should have been mentioned in the safety section. We imported Rex Precision, just the facility.
Okay, so the reason I bring that up is because you have a design where you're going to need to either attempt to load fuel into a concentric tank right out of the oxygen.
Yeah.
Or oxygen clean a tank that has fuel in it.
Yes. So this is something that has come up before. I didn't remember to put it in the slide, but the method of fuel loading is a intended kind of thing. Right now, what I've heard other people do and works is you get some kind of hand pump. You disconnect the fuel from the chamber and connect it to a pump, and then you pump fuel in, and at the same time it pushes the fuel up, so you don't get any air in there. We have not explored if this would physically work, but allegedly it does. So we will, and if it doesn't work, we can try something.
We've discussed other options such as, since we still have that piston and we have various places for vents and pressure, we have to test this, but we workshopped the idea of maybe using negative pressure from the oxidizer while the front of the fuel feed is hooked up to a source. So we could use the negative pressure on the piston to sort of suck up fuel into the tank like a syringe while it maintains the seal. So that's another idea that we can test.
Yeah. There's a, yeah, sorry. go ahead. Oh, I was just gonna say there's an exciting option.
Have you guys, if you have your factors of safety calculations for chamber pressure, tank pressure, okay, your radio? That's
Yeah. Yeah, that is, that's all in here. You can, wait, where? Oh, here it is. MIA, factors of safety factor, this is actually how we do this, sorry. But this is the MIA, and that's the design burst pressure. And as you can see, the design burst pressure is very close to where it would burst in the hoop, which is less ideal, but it is still lower than the hoop burst pressure, which means it would burst. Did we talk about this?
It was in the beginning, but
yeah, we don't want the tank to burst. That's the worst way it could burst. Because hoop bursting is when it bursts out. And any other bursting that it bursts upwards means there's less chance of shrapnel in.
We would rather fire the bulkhead up than fire shrapnel out.
Yeah.
So you're gonna consider sign up better for the factor safety, 1.163.
Well, that's 1.1 on top of the proof pressure.
It's 2.
It will be 2. It'll be 2 on top of the MEOC, but this is set above the proof pressure, so it's a little weird.
Yeah. It's like a factor of safety on a factor of safety.
Yeah.
It's
the proof pressure is what we will bring it up to in a test to prove that it is safe. And then the burst pressure, we will either burst it in a test to see if it is where we think it is, or we will be confident that it would.
We'll talk more about that later. Do we have one more question?
Yeah, just what does VL mean? Sorry.
Maximum expected operating pressure.
Yes, it's kind of, I don't, sounds good. We have one from Dr. Gray, and he says, have you explored renting one of the U of A food trucks? We have, and it is expensive. It is much cheaper to just use people's cars than everything.
What do you mean by first thing?
So what we do, we'll get into this in the later section, but to test the tanks before we fill them up with propellant, we fill them up with water. And the water is incompressible, so we can pressurize it safely to high pressures. And then when it does burst, it won't do so extremely energetic, like it would if it was filled with nitrous, which is, you know, I mean, I believe like plenty, like we talked about how many slides ago. But yeah. Anything?
So this is, we should have factor of safety of the tank if you have similar food radio.
That is what it's for. This is all for, this whole section is what we want it to burst at, and then how many volts do we need for a shear failure? How many volts do we need for a tear out failure? Minimum at that pressure. More would have those.
This the air to be fast.
It's for the concentric tank, correct? So it has, let me see here, main tank and inner tank. The main tank is the one on the outside, and that holds the pressure.
Pressure is against ambient as well.
Yeah.
On the inside, it is using the nitrous as the pressure. So they are roughly, there shouldn't be a significant delta across the wall of that inner tank.
We model about 15 psi, which is atmospheric pressure. It's very not. Anything else? Okay. Oh wait, we're on the wrong side. Anything else? Okay. Now it's 8:12. Right.
So the rectangle is our onboard, not exactly a flight computer because we don't do significant attitude control, but the rectangle is designed to collect data and do some light control for RCM. So we'll be collecting pressure data from our pressure transducers, which you may have seen in the PID diagram. So that gets our chamber, tank, and ground support will separately collect the bottle pressure. We'll also have sensors for GPS as well as inertial, barometric altitude, and then status of various valves because this is also the system commanding the onboard valves. And generally also flight state so we can have a ground link to be able to tell what it's doing. On the right side here, you can see some specifics about roll control and our reaction control valves. And it is commanding all of the onboard valves, which includes those at the top, which we'll talk a little bit more about there. But we're using the things like our different gyros and inertial measurement systems to be able to control the roll of the rocket. Now, we don't need that roll control for explicit stability. It is already going to be passively stable via aerodynamics with our fins in the back and the weight distribution. The roll control is more or less just a sort of experiment for our club and will provide nicer camera footage to keep the cameras stable as we go up. So that isn't necessary, but it is something that we're going to try and do with this computer. So that's why we have these extra sensors. And it'll be on top of it. Another page of requirements, wall of text, I apologize. But more requirements are things like actually being able to communicate via radio. So we'll have a ground station via a laptop or Raspberry Pi, whatever we like, some sort of computer that we can use radio to communicate remotely. We want it to have a long battery life, but it will also be connected to ground power while we're at the site, because sometimes we have to wait a while for maybe another team, maybe we need to do some fixing, maybe whatever happens. And so we'll be able to have some sort of quick disconnect for power to keep the batteries topped off. Meanwhile, while we go up, it'll log and record the flight data and keep that on for a while. So maybe while we approach the rocket, we can verify everything is dead pressure-wise. Otherwise, what else we got here? Remote commands for starting on more cameras, which is more straightforward, which we can worry about later. Otherwise, that is it for this page. Let me describe some of the components that we have. So for starters, LiPo battery. We haven't picked a cell count yet, but somewhere in the range of 1 to 3S. I'm leaning towards 3S because our onboard pressure transducers like a supply of between 9 to 12 volts-ish to be good reading. For our main microcontroller, we've decided to use the STM32, which has a lot of I/O and is very programmable, similar to Arduino, Raspberry Pi. Radio link we're going to use. We haven't finalized this one yet because there's a lot of various factors to consider with a radio system. But we're planning to use something similar, if not the RF900X, which is, this model is a 1 watt model, which is approaching the legal limits of what we can do without a hamster. And that will communicate with, depending on our antenna setup, could give us maybe up to 40 kilometers range, which would be great to have actual remote data while we're still in the air. SD card for logging data, it'll command the valves, which you saw from Jeff. These ones at the bottom are those specifics about gyros. The most important thing to note here is that we have 2 sets of gyros. One will be a low G gyro, which is a 9-axis higher precision, but it only goes up to 16 Gs. So in theory, we shouldn't really be getting to the limits of this, but it is very common in other flight computer rocket setups to have a second redundant gyro that is at a higher G reading. So we have another one that is 3 axes, which still give us those the various axes of rotation, but at a much higher G count. So even if we have a harsh recovery, for example, parachutes are deploying strong, we get a lot of acceleration, we'll still have some solid data that we can play through just in case this one reaches its limit. GPS here is a very standard one, used in a lot of remote vehicles, aircraft, etc. We have the option to use an external antenna if we find that the onboard one has bad reception. That last module there, an analog DC reader, it just converts the voltage from the pressure transducer into something digital that a microcontroller can interpret, read. Fortunately, they are very linear, very easy processing wise. And all of these, we've noted the rates of measurement, but that we don't need to talk about that here. Are there any questions about this onboard electronics?
Awesome.
Yes.
Do you have, just to get it out, do you have that, all the parts yet, or do you still need?
No. So we're planning to order everything that we need to manufacture at the critical, or after a successful critical design review. Right now, we're still working on some prototypes for PCB design, layouts, schematics. There's a lot of things that we will need to add to make a successful PCB. For example, USB port to program resistors, capacitors to regularly power throughout the various modules. So at that moment, we don't have a full PCB, but by the time we do critical, we should be ready for that and order all the parts.
Okay.
Yes.
So if you said this, but is the data recorded locally?
Yes, we will be using either a micro SD or if we find something better, maybe a flash chip, but most likely a micro SD card that we can disconnect when we want. Yes.
Is everything that you're doing an online system or it can work as well whilst you're offline?
So, so the radio that you saw here is the link purely between the rocket and some sort of laptop on the ground. So any sort of interface that you might see, like a website or something, would be hosted locally just to view the data that we get. So you don't need internet connection to read any of this information. The laptop is really just the easiest way to hook up one of these devices, and then you could run a program on the laptop to then interpret the serial that you're getting from the chip, which is all microcontroller, digital stuff. You can then just put a program on the computer to read it like you would a USB drive or a mouse, something simple, no internet required. Next up, reaction control.
Any other questions?
Awesome.
Okay. Hello, it's me again. I made that joke before. So, the reaction control system. This is the only system on the rocket that is not essential for flight. I want to make that very clear. If this system gets too complex or expensive, or it doesn't work when the rocket launches, that's okay. So, the reaction control system it's a system that you see in all kinds of spacecraft and like rockets, where you use small thrusters, among other things, to change the attitude of the rocket. And what that means for us is we're going to be using small thrusters to change the roll of the rocket. The reason we want that is because rockets have a tendency to spin a lot due to any like minor asymmetry in the design. It will just start spinning like crazy. And there's nothing wrong with that from a flight dynamics perspective. The rocket will probably fly straighter if it's spinning to some degree. But we want to do this as a proof of concept for something, something more exciting for us to do. And so as you can read these requirements, there will be 5-pound thrusters compared to the 1,000 pounds of the engine. So it will not be, excuse me, they will not be using a significant amount of the nitrous oxide, which it is connected to, so we don't have a separate gas supply, which will be very heavy. We'll be using some, it's not insignificant, it's just not a whole lot. We'll use the servo-actuated ball valves we have experience with. The reason we chose these is because they're very reliable and we know how they work. They're higher flow than solenoids, but that's probably not required. But we can use a more smooth control system rather than a bang-bang system you would get on solenoid. It will be controlled by the rectangle, two opposing pairs so that you don't have a pinch or yaw moment develop, only roll, which means the trajectory of the rocket is not affected. I should have moved to this slide earlier. Well, you know this. So these are two prototypes. Version 1, 50 pounds thruster. Turns out 50 pounds is way more than you need. So we downsized to 5 pounds. This is a 1/4 NPT cap, costs $2 on McMaster-Carr. It comes with this hole drilled in it, so we just have to drill that hole and it becomes a thruster. This is the last slide I have about the reaction control system. There's a lot more development yet to be done, but again, I must insist, it is not a critical system of the rocket. It is just an extended development for us that we hopefully should have, I hope, the time and the money for. So, any questions? I didn't cover it very deeply, but ask away.
So like, assuming the rocket is still spinning after the initial 8-second burn, this would have like enough fuel to stabilize after the 8 seconds? Or-
Yes, so
I assume it doesn't.
this is sort of a concern about the design that you sort of brought up. That this works off of the nitrous oxide gas in the tank, which there will always be some nitrous oxide gas during the burn, but there wouldn't necessarily be nitrous gas after the burn because it would all go out at the end of it. So in principle, for this to work also during the coast of the rocket, you have to shut the main valves, which that's probably one of the sketchiest things you can do, because that means you have the risk of a closed pressure vessel upon the rocket landing, which makes it more dangerous to approach. We will have lots of ways to monitor this. And ideally, if the reaction control under the programming, the reaction control thrusters open and they don't close, they only modulate how much they're open. But you can never guarantee these things. So there will be much proper safety procedures and proper like edge cases coded, meaning how this will work. And hopefully it will be, it's redundant also. If one of the thrusters fails closed, it will just spin the rocket and eventually drain all the pressure, and then it will be fine. But yes, that is a good point.
Just a follow-up question.
Yeah.
It would be located in the bottom, middle.
It would be located directly above the tank. That's one of the reasons for the concentric tank design is it allows the liquid output at the bottom and the gas output at the top. And so we'll have the reaction control thrusters here, and then directly above that will be the rectangle. And that will be reading the pressure transducer in the tank, will be controlling the valves, and it will also have a wire that goes down to the main valves and the chamber pressure transducer. But yes, that's the idea.
I have a lot. Okay, so, quick question on that. So understand, RCS is optional for the role standpoint, but we've also required that in defense. So if it doesn't, how do you reconcile, anti-detention?
Well, there's always the manual dump valve. That will,
Which is the one with the string, that must be.
if the last string we used was about 100 feet long.
You're making an assumption that the end of the string is fine. So,
True. No matter what happens, well, yeah, it is possible that we end up in a situation with all of the valves closed and the tank is perfect and it's not leaking. And we're holding on to pressure. We will have lots of systems to try to make this never happen. But if it comes down to it, and for example, if we take the reaction control system out, we will remove the valves, probably plug one of the holes, and then we will replace it with a static, which will be always venting out a small amount of pressure with like a 1 millimeter orifice, which is what we have on this rocket, which is a huge, very important safety feature.
It's difficult to see, but the static vent on this rocket is a small hole right here, which is why we have the tape here.
Yeah, put the tape so we can find it.
Yeah.
you're saying the right things, that's one which you.
Yeah, it's absolutely a severe failure case, which we'll need to consider. I suppose worst case, if we do test and we prove that our servos have some amount of unreliability and could close, leaving a pressurized vessel, we might have to include a static vent, which would be unfortunate, but
It would be bad for performance, but it would be good for safety.
yeah, we would need it for, yeah.
And
I just would expect that follow.
Absolutely. As we develop this, we'll have to keep that in mind. Thank you.
If there is a severe lapse in judgment, I have heard of other methods of rapidly depressurizing. Yeah.
Before I pass my question, shoot it with that point too.
Yeah, that's that. Yes, yes.
Let's discuss that. Anyway,
It's happened before.
Yeah.
I figured, anyway, you've already ruled out like a small separate tank, because there's probably not room for that, and it's probably ineffective.
There would be room, like room could be made, but the biggest concern is mass. You would need a lot of gas, whatever you choose, to effectively control the rocket. I mean, you could do the math on that. Like, what if the rocket has one of the fins set like that, and then it spins? You know, what is the maximum you would need? And it would be a lot. It would be heavy, and it would be high pressure, and it would be, importantly, another fluid system that we don't want to have to deal with.
I have somewhat two suggestions to the
Okay.
one, a grounded one, to make things simpler for safety, one very cool one, to make things fun and exciting.
Okay.
Okay.
So the ground one for safety, I definitely raised my eyebrow, and I noticed that you're selecting sort of actually the ball valves, but in our CS system.
Mhm.
To-
Oh, are you talking about freezing?
Freezing is gonna be less of a concern if you're not fully liquid.
Yeah,
That's a
true.
concern for your main valves, but I'm trusting that your experience with happening is going to provide a concept of that. But it seems to me that solenoids are a natural fit for this, because for one, they can be made lighter and smaller than these new ball valves. And two, and this is perhaps the biggest one, they can be made so that they fail open.
This is
They
true.
require currents to keep closed, and if you're worried about, not being able to, if you're worried about like getting that in a situation where you have pressure in the rocket after recovery, this would be a good solution to that. So just wait until the battery loses power. Worst case scenario is
Great.
probably lose power by the time it takes you class and things like that.
Yeah.
Time this in 2 hours, and then you have
Well,
and
assuming we keep like, but yeah.
yeah, and then that's it. Also, solenoids are going to give you a much faster response time. I understand the appeal of having a finer control over the amount. It's how with ball valves, it's worth to remember, unless you get very specific kinds of ball valves, they open very, they go from not closed at all to a good amount of fluid very quickly.
Yes, that's definitely true.
So I would look into solenoids like I know the bang bang seems like it would be less, right? It seems like it'd be less control over but they can close so quickly, you can write control algorithms to very much.
Like pulse width, yeah.
The big thing, well, I don't know about pulse width, but the big thing I was also worried about with solenoids was their dead that you would get because you would have some minimum rotational impulse that you can provide, and with it, you would just end up with a slow rotation, which is fine. Like, but if we want to maintain a hit, it would be less cool for them.
You do need to, but there are, if you want to do this, there are a great example, but there are specific ball valves with like weird U-shaped reliefs that are designed for very fine control over one of the sides.
Interesting.
You don't go stand ball valves, so maybe look into that. I still like solenoids. Now, to stopping in Killjoy, I do just want to point out that the nitrous oxide is considered to be is used in a lot of our CS thrusters, space industry, because it's it can be decomposed. There are certain catalysts which can decompose nitrous oxide into nitrogen oxide and give you double the gas volume and higher temperature. And the nice thing about catalysts is that there's no moving parts to this. They're a natural fit for our CS thrusters.
I thought
Like I said, an exciting and cool idea. There's probably another good one.
Yeah, I thought about it. It would be exciting and cool, and it would also be playing with nitrous decomposition, which you know what Rick says about that. It's a positive enthalpy reaction. It could spread. I don't know. Yeah, I agree. It would be cool. Maybe it's a version 2 kind of thing. if we want to get into pitching our controller, we need the extra thrust. Which, all right. Any other questions? Yes.
Sorry, I have another question. Like, I'm really unfamiliar with this rocket. When you say you're like controlling the rotation, you kind of like pointed the thrusters like this. So you're assuming it's only going to be rotating clockwise.
There are two sets.
There would be two
Okay,
sets.
Yeah, so we would have opposing pairs.
I
So-
think if it's set up like an H, where the points of the H is
Yeah.
out of the.
Yeah, each valve controls one pair that would rotate it either counterclockwise or counterclockwise. So you have one pair would be like this and controlled by the same valve, so you wouldn't have any weird unequal yaw moment. Then the other one would be same thing on the other direction.
Perfect. Thank you.
Yes.
The expression.
Yes.
Okay, so for GSE, we're basically gonna be using the same thing we had for this one for the new rocket, so we're not gonna be making any, like, we're not restarting and building from the ground up, we're gonna use our same box, same electronics, same thing. With the same goals, which is, controlling manifold and GC vent valves, monitor report oil pressure, and, control using our wireless telemetry. So I'm gonna talk about some of our main upgrades, plans for it. So, I'll start with, so for the wireless telemetry, right now we're using an RC controller to control our valves. We're eventually going to change it and use a graphical interface on a Raspberry Pi. So we can just kind of like click buttons, and this will kind of, this will hopefully solve some problems like, we have had failed static fires where we didn't realize that we had to offset how we could do, I think it was throttle and ignition at the same time. We did it at the same time, and it ended up not lighting, so we realized we have to offset them a little bit, which is, pressure for the person doing that. So if we have something like this, we could maybe program it so that it does that for us, so we don't have to worry about stuff like that. We could also have like our pressure data on there, so you can kind of see, have it tell us when it's ready to be fired, all that kind of stuff. And just make it look nicer. We have a whole RC controller for just a couple switches. Now we might need to use that. Also, it's technically all ours. So, yeah. And for monitoring and reporting our bottle pressure, we have a whole data acquisition set up right now with our electronics. And we're currently upgrading that, just making it better, making it work more reliably. So I guess go to the next slide. So, biggest change we've been working with right now is this PCBI design in the summer. There's a few goals in my mind. I designed this organization, solving problems within what we have. So for organization, we have a lot of like terminals and things, so we can see much easier where things are, if things are disconnected. We used to have, it was like a lot of wires, they were very long, and it was sometimes hard to tell if these were disconnected on purpose or not, or,
It's on the next slide, actually, I believe.
Oh, yeah, actually, if you go to that slide really quick, you can see, this is most recent, not done at all, but this is, one of our static bars from last semester. It's kind of hard to see, but there's a lot more going on in there. It's a lot more complicated. So, if you go back to the other slide, this is meant to simplify everything and just make everything look clear so that we can identify problems and solve them quickly. There's another couple things that this PC will do. So, for example, our receiver provides power to all our servos in our relay, which is not great because it's a very thin wire. It's only one thin wire that supplies all the power, which could be a risk for, if we're using multiple servos at the same time. There could be a voltage drop, and our servos might not react as quickly as we need them to. So, the solution for this is we have our receiver connected onto these pins, and then it sends the signal to these pins, but the power actually comes from here. So we can have the power from here, but the signal from here. So then we have, all the other components connected on there. So we have really reliable power source. And then we have fuses and diodes on here to prevent damage to the board and other electronics. And another kind of problem this aims to solve is we had an issue with our, when we ignited our rocket, the relay would close and it would draw so much current, it would cause a brownout in all of our electronics. And so our Raspberry Pi that sends the data over to us would die. And when it dies, it takes 90 seconds to reboot. So we would have 90 seconds without data, which is bad because we want to see the pressure data during the fire. So we originally solved that with an ultra battery, but with this we have put resistor in series with it, so that it doesn't draw so much current. And we're currently testing this still. We know that it'll ignite the igniters, but I don't know if we've not quite got it to work, but we're still having full resistance. So we'll do that, and we'll hopefully solve that problem. And it also, go to the next slide. So this also eliminates the need for repetitive use of components. We used to have like a lot of extra stuff going on, mostly because we were just upgrading things as we went last year. So there were actually quite a few things in that original design that we didn't use anyways. They were just there. We just didn't really, why not? Even though it's a big box, we didn't really need to take it out. But there were some things like we had 5 voltage regulators, and there were like 2 of them did the exact same thing. But so for this design, like we only need 2. I haven't taken that one, but it only needs to do it once. We have control of that. We have 2 because one runs 5 volts, 5 volts. Anyways, so just organizes everything. And also, just kind of cool fun upgrades like from pressure transducer cables, instead of having them directly screwed into our DAC and having them rip at the terminals all the time and having a big risk of them falling out or breaking the wires and stuff, we have like a connect thing where we solder onto these little connect pieces and they just screw into this, and then we would screw these in here, and from the PCB design, it connects there so that the data can go through there. Making it so we can store our pressure transducer cables separate and not have more risk of like damage in the box from having extra materials in there. It's also reduces safety risks, like having an extra battery. There's just more risk. Having exposed terminals is not a safe thing to do. So we want to only have it in one place if possible. But yeah. So, and then I guess the little stick, the CPU link and the little legs thingy, that's what is our wireless Ethernet for our data. And I think, we're still figuring things out. We have a couple different uses for Raspberry Pi right now. One is only used for the data acquisition. One is what I've been using for testing on this. We're probably going to combine those 2 and have it do the same thing. So we only have to have one. And then, so this is just more upgrades and it'll mostly remain like the same ideas. Yes?
Is this moving forward, like, is this just a preset that you can buy somewhere, and you have to design a circuit that has to, how do I specifically design it? That would be well.
Yeah, so I designed that one on PCAD, just some PCB CAD software. And then there's different things you need to do, and like to get it ready and send it off to a manufacturer. The way I did it, I just had them print my board and design, and I bought all the components separately so that I could do it myself because it's more expensive to buy their pieces and then have them solder stuff in. Also the board is very flexible because you can solder it like I was showing with the pins where you put the receivers. You can have power from the receiver go to the servos, or you could have it where the battery supplies power. So I wanted to be able to choose if I wanted to solder those resistors on or not. So I didn't have them do that. But this is just my own design. But yeah, there's no intelligence on this, just all questions.
So you mentioned about using Raspberry Pi. Which Raspberry Pi do you use?
I can't remember which ones.
There are 2 that are in use. The old one, which we used at our prior static fires, which was solely for that data acquisition, that was a Pi 3B. Yours, I believe,
I can't remember which one.
I think it might be a 4B plus.
And following that question, why why not Raspberry Pi? Why not an ESP32 or STM?
I don't really know what those numbers and things are. I just know that Raspberry Pi is, just common to use,
I can jump.
relatively simple to program, and I'd be students programming what it uses, so I just use that.
I can finish that. For our prior setup that we used at the competition, the little blue box, if you go back one slide, I think, this little box here was our DAC system, which converted the pressure transducers to digital. And that has a USB connection, which is very difficult to do over radio. So what we used the Raspberry Pi to do was convert this USB signal, as if it were a computer, into something that we can then send as an Ethernet packet. And that would then go through this wireless bridge, which was commercial off the shelf, simple system. It just worked. And so that whole setup, as you see here, I would just basically forward this USB connection as if it were connected to a laptop. The future plans could keep that or do onboard analog conversion. So something like an ESP32 could be in order to connect to the Pi, or we could do that onboard.
Yep.
Do you still have that, or do you possibly need a new one?
And what?
We have it. The whole box is in our lab.
Okay.
Yeah.
All right.
Yeah,
We can
yeah.
take a look at it later.
Okay.
Yeah.
All right.
Next, I believe is.
All right.
Yeah, pass me my bag.
You guys aren't gonna believe what you're
Are you up next?
So this is actually the shortest section. The structure of the rocket is going to be functionally identical on the new rocket versus the old rocket. We're going to use these bolted L brackets to connect between the tank and the engine. The fins will be bolted onto the L brackets. The only thing that's different is that we won't be using these angle brackets. We're going to bolt sort of more directly to the engine with like a big spacing. And that's basically what it says. We want to design from the beginning the ability to cover it for aerodynamics because, it's free extra performance if you can do that. And we also require that it's easy to disassemble, specifically taking the engine section off of the tank, because the tank is the longest part of the rocket by far. And so it's just a logistics thing to transport. This slide is now sort of redundant because we have the rocket in front of us, but this is what we're talking about. You see these L brackets here that connect two bolts to the tank, and there's space among that for pipes and for pressure transducers and valves, things of that nature, and then it bolts to the end. All right. Any questions?
For the space, the next one, will you still cover the space or you keep it moving just as it is?
Hopefully we'll cover it. We want to, from the beginning, make sure it's possible to be covered. This, as you can see right now, there's a lot of things that kind of stick out and make it a pain, but we want to, think of that. Yeah.
I guess two things to ask. Well, it would have to be metal, right? Cover would have to be metal, right?
Maybe.
We don't want it to collapse on itself.
If it's
The cover won't be structural. It'll just be for aerodynamics.
in which case we could do
It
some.
could be 3D
composite.
printed, but the engine might get hot enough to make that a problem.
Yeah.
If not, we can do composites. We have unlocked making our own composites now.
Which
So
will happen in recovery review when that happens.
yeah, but
But
so yeah.
we got options.
I was gonna ask pretty much the same question, like, could it be aluminum or,
It'll probably be aluminum.
yeah, or something like a fiberglass shell that's then carbon fiber. I know that's
Oh, we mean
ridiculously expensive.
The shell.
the shell. It could be 3D printed or it could be fiberglass. I think those are the two most likely. Anything else? All right. Steam burning. All right. Testing. This is actually more interesting. Maybe this should have been higher in the presentation. So, before we fly the rocket, we have to test it. We have to know that it will work before we spend a bunch of effort and try to send it a competition, but there's a lot of pressure. So the competition rules specify tests we have to complete and a deadline. Yep, the deadline we have to do it by, which includes hydrostatic pressure proof tests, which we'll get into what it includes because there's a slide on there. Of course, safety is very important. Testing and flying are probably the two most dangerous parts of doing rockets, but also the two most exciting. So it's kind of a trade-off. The competition only requires one static firing. Our goal is two, just because you never, with one you can have a fluke and you might not realize. With two, you have a little better idea. Problem is, static fires are expensive. The consumable cost of nitrous oxide is, we expect about to consume 56 pounds of nitrous oxide per firing, maybe more. And at the local rates, a pound of nitrous oxide is $11. So it adds up fast. Yeah. It's also, of course, expensive in effort in getting it to work. So here's the different tests we do. Pressure proof test. This is the most preliminary test, I guess, where all of the pressure vessels we build, they're sealed, they're filled with water, and pressurized to 1.5 times the maximum expected operating pressure. We use water because water is incompressible and in general will not explode if the tank were to fail, as opposed to nitrous oxide, which would go crazy if the tank failed.
Or even CO2.
Even CO2. CO2 is often used as an analog for nitrous oxide because it has similar vapor, like pressure curves and everything, but it's not an oxidizer, so it's a little safer. Anyways, injector flow test. This is actually probably one of the safest tests we have to do because it only involves water at low-ish pressures. I think it's pressures you could get from having a bucket with a hose going down and holding it at the top of the any building bridge. But it's basically, the idea is we hook up water to the injector and then we measure the pressure in the manifold of the injector and then let water flow through for a set amount of time. So we know what the water flow rate is through the injector, and that allows us to know what the discharge coefficient of the injector holes is. Also, static fire, the most fun kind of test other than launch. The entire propulsion system is set up as it would be for flight, with a few changes like mounting the engine horizontally so it doesn't pick up a lot of dust. And, we have an I-beam, so going horizontally, I-beam makes a lot of sense. You know, it's an all-up test of the entire propulsion system. Reaction control spin test. This will also be interesting. We'll use a small version of the tank, probably the version we do pressure proof test on, and we will hook up the RCS thrusters and the entire forward bulkhead assembly with thrusters and the rectangle, and we fill it up with nitrous oxide and you know, just play with the valves and see what the IMU measures for how rotates. And that allows us to characterize what force are we actually getting out of the thrusters. And then we can, you know, back out a stronger control system for that. Range test. This is, oh, I lied. This is actually the same as all it involves is all of our radios. We need to make sure they work at long distances. So we go long distance and see if they're rectangle test flight. This is not a strict requirement, but it would be a good idea where we have the rectangle computer ride on a smaller rocket, like a solid rocket, and it gathers data, it transmits to the best of its ability, and we make sure it works. So, testing. This is how we've tested the rocket in the past. This picture is this propulsion system at FAR, the Friends of Amateur Rocketry, mounted on an I-beam for a static fire test. This is the rocket firing, you know, with an incredible camera angle. I love it so much. And this is sort of what the I-beam looks like without the rocket. We have, the I-beam has a bunch of holes in it, and we added this extra little thing to hold the rocket. It worked pretty well. There were some sketchy things about the design, but it was fine. Actually. We tested it twice. at
Two
Bar.
successful fires.
We had a third unsuccessful fire because the valve got stuck. But we pulled the nut down. It was used. So we also have a new idea. This is down in Sarita. It's a test site that we just constructed last month, and it's a gigantic I-beam that's concreted into the ground, and it has holes in it that we can mount the rocket to, and we can do test firings. We haven't done any yet, but hopefully we will soon. We're mostly experimenting to sort nitrous oxide. This stuff, so
We have
But-
fired once at this site, but we haven't fired it on this I-beam. So we
Yeah.
know the site is good and the place is fine.
the site, a thing I should point out, this frame right here is very compressed. It's a long focal length lens. I took this picture from very far away. You can tell because there's no sky. It's just the mine tailings pile in the background. So this foliage and everything, this is much further from the I-beam than it was. Additionally, the I-beam is oriented towards this pile of rocks down here, which is much bigger than you can see. And since the engine will be firing towards the pile of rocks. In event that the nozzle blows out or if something happens bad to the engine, it will shoot at the pile of rocks, and that will hopefully absorb a lot of the energy rather than shooting into the brush and starting the fire. All right. Any questions? Yeah.
I'm just curious, if something does go wrong while testing, how hard is it to troubleshoot or maintain it? Rocket.
It really depends on the system. If it's an electrical failure, for example, we have a loss of communications, but the system still has power, then that, depending on how it's configured, could be a black box and could be just a situation where you pull the dump valve and figure it out after. If it's something like a leak, that we can also halt pressurization process if we're in the middle of fill, for example, or even before fill. For our testing campaign in this rocket, we would do a quick little check by just pressurizing the ground support first, and sometimes we would have to go back and double check and fix leaks. Sometimes we would also do that between firings. So it depends, but we have various criteria that we can kind of work around.
Yes.
Since you mentioned you having trouble or seasonality contract, so what are you?
So there's the best source we have for nitrous oxide, and you'll probably see immediately why this is a problem, is this company called SoCal Nitrous and Racing. And it is in Los Angeles. They have two locations, but it's minimum like 7 hours drive from. It's great. Whenever we go to Los Angeles, it's like a great opportunity to pick some up and take it home. The bottles are DOT rated, so they are safe to transport. But of course, you gotta be cautious when doing that, or put it in a truck then or something like that. But there are racing shops in Tucson that will fill up nitrous bottles, but they won't rent nitrous bottles. And we don't own any nitrous bottles. We have to rent them from SoCal Nitrous, which we did last year. We rented them from California, brought them to Tucson, used them like for 2 firing attempts in between, filled them up, and then we had to return them. So nitrous bottles are also expensive. That's partly why we don't own it. Because pressure ratings are expensive. This is the whole thing.
All right. So, first of all, I'm assuming recovery tests not included.
Yes.
Yeah.
Excellent.
We have one upcoming actually very soon. That's why they haven't made it for this one.
Yeah, recovery team is very busy.
Awesome. I noticed that you did not have any cold flow tests in Team Argonauts.
Oh, that's true.
We could add that.
That might have just been an oversight, but we can add that, yeah.
It gives you a much better idea of what sort of pressures you're going to get with off of this pressure system, and you're going to get a very good simulation of the valve result.
True. Yeah.
So both of those things are using CO2, and it's a lot cheaper, and you can test it about.
Yep.
Speaking of which, have you talked to Rick about nitrous oxide supplies? I know he has a supply for a few years since I go.
I talked to James, and James says that you'd pay
It is a huge.
Because if you want to get it from a gas supply, because they specifically only sell to businesses. So the school has an account, but they won't let us get an